So Pamela, are you ready to your recording?
Okay, can everybody see my slides?
Perfect, perfect. So I'm Professor Adrian Murphy from Queen's University Belfast, and I'm going to introduce the next three speakers. And it's my great privilege to welcome Margaret Stack, who's Professor at Strathclyde University. So the floor is yours, Margaret.
Okay, all right. Thank you very much for the invitation to participate in such an interesting meeting. And obviously, okay, start. You can see. I just to say thanks very much for the invitation. Now,
Margaret, are your videos not on?
Pardon?
We'd like to see you if we can.
Yeah, I know. I'm trying to. You cannot start your video because the host has stopped it. That's what I'm getting here.
Okay.
Is there any?
Check now, Margaret. It must have asked you to start. Yeah.
Yeah.
Perfect.
Can you see me now? You can.
Yeah.
All right. Brilliant. Thanks very much. Okay. So I just today I would just like to speak about some work we've been doing in Strathclyde University, where I'm based, on materials, the study of erosion of materials in renewable energy systems. And what I'd like to talk about today is some of the work that we've been doing on erosion of wind and tidal turbines, and some perspectives on coating selection. Okay, so basically, if we look at our offshore wind turbine, we can see we have a situation whereby we've got a rotating system. Allan mentioned this, earlier on, where we've got we have problems with wear and erosion on the rotating system. Obviously, the erosion issue is going to be much greater at the leading edge, as the velocity increases. But from the perspective of the selection of coatings for these kinds of environments, some of the paint manufacturers up to very recently were not guaranteeing coatings above a certain blade length, and therefore these kinds of material solutions are still very pressing for these kinds of devices. Now, we've also got a combination of erosion and wear in these systems. Now, if we go to, okay, if we look at this image here, this is what happens on the surface. We get erosion at the leading edge of the blade, and problem is that in a non-shore system, changing or at least replacing the coating can be quite difficult, and sometimes very sort of patchwork solutions are being used. But if we're talking about an offshore system, the recoating a blade is a much trickier situation, but also it can cost a much more than obviously than in an onshore system. And we know that at the moment there's a huge driver for offshore wind at the moment, with recent auctions of sites in the British Channel and also in the Irish Sea. So that this is a kind of a big driver at the moment. Can we improve our coatings for erosion resistance? Okay, so if we just look at the microclimate for Britain, we can see that the rainfall annual average is obviously much greater in Scotland than in other parts of Britain in the southeast. And at the moment, the kinds of coatings that are being offered for protection of wind turbines do not necessarily take that into account. The fact that the attrition rate is much greater, can be much greater in the west of, or at least the northwest of the country, by comparison to somewhere down here. If we're talking about, in around Southampton, there's quite a large offshore wind project. Anybody who's flying into Southampton can see it. So therefore, we've got to think about the fact that one size fit for the microclimate that is presented just by the UK is not going to work. We have to think about optimizing our coatings for the different microclimates, and indeed that means that we need to think about coating selection tailored to the microclimate. Okay, so in COP, in some of the sort of descriptors of the aims of COP26, and this was mentioned earlier, that investment in renewables is obviously a very, very important issue, but also we have to think about what aspect of renewables, and I would suggest that in the materials side and in the coating side, there has been underinvestment, and we need to think in terms of reducing carbon emissions. We need to drive this issue much more than in the past. And obviously the roadmaps that Barbara showed earlier demonstrate that these issues are being considered, but the reality is that on the ground, there's still a lot of work to be done. Okay, so I think in some of the storms this summer, there were reported very significant hail events. And if you look at the days of hail on the annual average, you can see again, much greater hail in the northwest of the country and parts of Northern Ireland by comparison to that's close to sort of Derry and places like that. Even, you know, there's quite a difference by comparison to Belfast. And indeed, obviously, in the northwest of Scotland here, you can see that very much higher rates of hail. Now, the hail is an erosive component. It will degrade the coating on the wind turbine, and obviously that's going to be an issue in terms of the degradation of the coating. Now, what does the coating do on the turbine? Coating means the coating protects the structure, but also it promotes, or at least a smooth coating will promote aerodynamic efficiency. And so therefore the efficiency of the overall process is going to be dependent on how smooth the coating is and how aerodynamically efficient the coating is as it, or at least the blade is as it rotates, or at least through the air. Okay, so basically, just going to talk a little bit about tidal turbines. Tidal, because the density of water is approximately 1,000 times of air, that of air rather, tidal turbines at much lower blade length endure erosion and at the leading edges, and also endure cavitation. So, and this is a sort of the formation collapse of bubbles on the surface. Now, this tidal energy is obviously a very constant source of energy, predictable source of energy, but still the application of tidal turbine energy is being limited by the performance of materials and coatings. There's still quite a lot of work to be done in this area in order to drive forward this technology. And essentially at these very high thrust loads at the leading edge of the blades, the turbines break down, and there have been many many companies have been deploying new and more higher grade composite materials. There's one instance in the Bay of Fundy a few years ago and they've lost many turbines in these testing environments as a result of the fact the high degradation due to erosion and cavitation. Okay, so what are the tribological issues? In tidal energy, we have velocity, the load, also the temperature. We're just talking, we have to think about these turbines can be exposed to quite icy conditions, but also we in other countries, obviously we have the opposite situation where we've got rather warm environments, and we have to take that into consideration as well in terms of the reaction to the material in those environments and any expansion that might occur of the polymer. For erosion, we have the various parameters associated with the particles. Say, for example, if it's a sand particle, the shape, the size, and the concentration, and the hardness, and sometimes the say, for example, if the sand is covered by some sort of a corrosion, a substance, say, for example, if there are any sort of pollutants in the water, for example, sulfates or whatever, that can cause corrosion. We also have corrosion, seawater affecting the erosion on the surface and interacting, and there's a whole science of erosion corrosion, or at least mechanistic interactions, and the impact angle that the surface presents to the particle. And obviously there's things like the mechanical properties such as the yield strength and the toughness. Okay, so the corrosion conditions, I think at least the electrochemical potential, the hydrogen ion concentration, the pH, and things like the concentration of, say, the chloride on the surface, and then any alloying additions. And in terms of a coating, whether the coating is the composition of the coating, whether it's a polymer-based coating or it's a metallic-based, and also hybrid, or is it a multi-layered structure, etc. So basically, what my group has been doing for many years, this is just an example of erosion corrosion of pipe. We've got the pipe eroded at least the bend that's associated with the high concentrations of particles. But what my group has been doing is to combine the Pourbaix diagram. This is electrochemical potential versus hydrogen ion concentration, and these are the various corrosion regimes. This is where we get to iron dissolving. This is passivation. With the Lim and Ashby, Mike Ashby's group in Cambridge developed this Wear map in 1987. And what we've been doing, and these are kind of various regimes associated with the sliding wear phenomena of two metals on the surface, and resulting in oxidation on the surface, oxidational wear here, which is not very beneficial, but quite beneficial here is severe oxidational wear, where we get the formation of a so-called glaze layer on the surface, which reduces wear. So different regimes of wear. So the work that I've been doing really is to kind of combine these kinds of the corrosion with the wear, and define regimes of interaction for erosion corrosion to form an erosion corrosion map. This work was did in Manchester many years ago, but basically combining the tribology with the aqueous corrosion in this kind of a diagram. Okay, so for low carbon energy technologies, we've got a range of devices, and we have a multi-parameter issue. We need to think about designing materials for microclimates. I just showed you the map earlier on. And then we have to think about smart materials for structures, as I said, hybrids, functionally great materials, coatings, and composites. And then I think it was mentioned earlier, the weight per energy efficiency and versus the degradation rate. So those kinds of, all of these kinds of issues are important in terms of designing for the low carbon technologies. So this is the example of the erosion corrosion of the pipe again. What we have been aiming to do is to combine a map, or this 2D map, into a 3D space here on the surface. So we identify the erosion corrosion regime on the map, and then we've modeled it so that we can see the change in the pH on the surface. So if we look at the rainfall annual average again on this on our weather map, and our days of hail, also again very high number of events in the northwest of the country, and then our offshore wind turbine. What we would like to do is to, or rather, we would like to do is to map the performance over that turbine. Okay, and again with our tidal turbine. Okay, so what are the tidal energy resources in Scotland? We have two main sources, and one of them is the Sound of Islay here, where we have tidal energy farm, and this is the Pentland Firth. Okay, so this is a map which will give us the kind of the optimum conditions for extraction of tidal energy. So what we've been doing in terms of our research collaborations, we've had a number of grants funded, one of which was it was RECASM, which is reducing the cost of advanced materials specifically for tidal turbine materials, and that was a collaboration between ourselves, Southampton, and Newcastle. And there we built erosion corrosion rigs for simulating erosion of the tidal turbine conditions, and looked at the performance of various polymer-based coatings, as well as some just steel materials and composites. So we also have had other funding in recent times. We've had a grant funded, it was on energy storage, and energy storage was mentioned earlier as well, the importance of energy storage. We're the group that is testing the performance of wind turbines and tidal turbines as part of the Part-2 project, which is it's a very large energy storage EU project, which is led by the University of Ulster and collaborators in Queen's, ourselves, and Dundalk Institute of Technology. Now, I think it was Artlis Laura mentioned earlier on, and was followed by Barbara in discussing sort of mapping and optimization. But the objective of this this grant was essentially to look at the energy independence in terms of renewable energy for the Highlands and Islands off the coast of Northern Ireland and Scotland. It's an Interreg project, and it's part of the Interreg funding in Northern Ireland. So basically, the idea is energy independence for smaller communities, but also energy storage is absolutely critical. I think the analogy between the refrigerators and if you didn't have if you didn't have your fridge, freezers, or whatever, what would supermarkets look like? They'd have to be much bigger consortia or whatever. So it's touching on the same theme that how we can if we can have a more decentralized renewable energy system, but also what are the kinds of things we would need to do in terms of optimizing the coatings for example, a small community who's running a wind turbine, optimizing the coating performance, and also the storage issue, which is a very, very significant issue. We're working on material solutions. That area is being covered by University of Ulster and Queen's. So that's basically what we've been doing, and we've also got an EPSOC project which links us with the University of Edinburgh and on different material solutions for different energy environments, including renewable energy as well. So these are the kind of different programs that my group has been involved in recent years. Okay, so I'm just going to talk a little bit about some of the work we did on tidal turbine simulator. This is just the apparatus here, and this is the kind of, we're just rotating the business through the system, and this is the simulation of the flow. And we looked at a composite material and also coated materials, the polymer-based coating. Sorry, on the right-hand side, it's not very clear the properties, but it's just a polymer-based coating. And these are the kinds of conditions. So I just want to just give you some results. What we found was that if we looked at two different sand grades, we found differences in the effective impact angle for the composite and the coating. So of course, not surprisingly, we get much higher erosion rates with our larger particles. Okay, so basically we've got these are just some or at least SEM images of the surface micrographs. What we found, what we developed as a result of our research was two series of maps, one for the composite and one for the coating. So we found that our coating performed in a ductile way, ductile erosion mode, but there were differences in the regimes. But for our composite, we got an environmentally assisted fatigue cracking on the surface at the higher impact angles and our size. So basically, what we saw in this regime here is that the presence of the chlorides, even in a composite, polymer-based composite, has actually caused an accelerated cracking regime. So these are the kinds of maps that we can generate for these kinds of conditions, coated and uncoated. And this is a wastage map here showing that obviously uncoated is it can cause or results in much greater wear than coated. Now, for the tidal turbines that have been materials that have been developed to date, and those materials that have been used on turbines that were deployed and tested in sort of at sea, so to speak, what they've been finding is this kind of regime. There has been catastrophic failure of these turbines. So obviously they need something like this. And some of them have had polymer-based coatings, but the coatings have not been protective enough. And now for these kinds of tests that have been carried out, I know of one company in particular because, through sort of word of mouth or whatever, because some of these test results don't really get disseminated, because if it's a positive result, but it's millions that you're talking about. Once they get to testing the turbine, it's absolutely millions. So when you think about the investment that could go into R&D to optimize these coatings, to improve them or whatever, and in terms of investment in a research project, it's really minuscule by comparison to the situation of a company deploying the turbine and finding that it disappears, and indeed many of them have disappeared because they haven't been robust enough. So
Margaret, can you close?
Okay, all right.
We're a bit tight on time.
Yeah, so basically, I'm just at the very end actually, so you've just caught me at the right time. So basically, if we just look at our two maps again, rain and hail, and we look at the average monthly rainfall for January and May, see a big difference, obviously. It's just a work that we produced earlier this year, and look at what we sort of a testing of a wind turbine. We can generate these maps for January and May for the erosion of the materials, and this is for raindrop erosion of wind turbines. So we can generate erosion maps for the materials, and we've included hail here. The most important thing is that in the different microclimates, you get much higher erosion on the materials. Okay, so basically, this is just to say, to conclude, the tribocorrosion issues are important in renewable energy technologies, and these renewable devices all undergo these kinds of tribological processes. The maps can provide a means of tailoring materials for the conditions, and I think, from discussions with Allan and or at least Gaurav and others, that surface engineering digitization can be combined with combined with these erosion maps to optimize coatings performance is something that could be addressed in future research projects. Sorry for just exceeding my time, and thank you for your attention. Thanks.
Thanks, Margaret. That was really, really interesting. Well, maybe for the panel, and we'll jump to the next speaker. So Dr. Neil McSporran comes from NSG Group, and he's going to talk next. And he's going to talk next, and he's going to start giving us the industrial perspective. So Neil, are you there? Can you start sharing your slides?
I am, yeah. Hi, everyone. Margaret, if you could stop sharing your slides, it won't let me override you, unfortunately.
That's fine.
You. Perfect. Thanks, guys. Hi, everyone. Nice to meet you all. So as was mentioned, I'm Neil McSporran from Pilkington, NSG. And I'm going to give a presentation on glass manufacture and thin film coatings. We'll talk a little bit about our products and how we manufacture those products, and then some of the applications in which the products are used, before focusing in on some of the key sustainability challenges that we have in glass manufacture. So just very brief introduction to NSG. So NSG is a large glass manufacturing company, one of the biggest in the world. The name in Europe is, of course, Pilkington. So NSG bought Pilkington in 2006, and yeah, we're present all over the world, and we have three main manufacturing areas. One is architectural, where we make a wide range of products, but of course, architectural glazing with low emissivity coatings, solar control coatings is a big part, as is glass for solar panels, where we make transparent conductive coatings for use in solar panels. We also are very active in automotive, where, of course, we have a number of glass products to improve range and sustainability of vehicles. And we also have a smaller technical glass division where we make things like battery separators and other materials. Probably won't have time to speak about those today, though. We are quite global. We're in every part of the world, really, with manufacturing and sales. And as you can imagine, each part of the world requires different products and different solutions. I'm responsible for the incubator within NSG, and that's where we develop a lot of our next generation technologies. So anything that involves new technology, typically anything with external collaborations with partners, are handled within the incubator. So just starting off by thinking about manufacturing. I don't know if you're all familiar with the glass manufacturing process, but it's a very energy intensive process. The temperatures there reach up to about 1600 Celsius, and that's because we have to melt raw materials to provide the glass, basically. So we melt a mixture of sand and other components like dolomite and limestone and others to produce glass. And a lot of that melting is carried out by gas firing, as you can see in the photograph that I'm showing there. And that enables us to produce very large, optically clear pieces of glass in a sheet width of about 3,200 millimeters. So that's also continuous. So before we cut it, it's a continuous stream of glass coming out of the furnace. The glass, is used in many products, but we really add functionality to that glass to provide different impact, really, by using our coatings. And we use two types of coatings. One, which we term online, which is chemical vapor deposition during the glass manufacturing process, and the other offline, which is typically sputtering, or PVD. We also operate some wet chemistry coatings like sol gel, but again, I won't be speaking about those today. I'll focus in on CVD and PVD. So chemical vapor deposition is probably our strongest technology, and with that, we actually deposit our coatings during the glass manufacturing process. Now, the challenge of that is that we're operating within the float bath, and it's, as I mentioned, you're coating on a continuous stream of glass, and you're putting down complicated multi-layer coating stacks on a continuous stream of glass at a very high temperature, typically around 600 to 700 Celsius. So as you can imagine, a high degree of monitoring and controllability is needed during the process. And we put down a number of materials using this process, some of which are electrically conductive for use in things like solar panels, and I'll speak about that in a second. Others are low emissivity coatings to keep rooms and buildings thermally insulated. Solar control coatings keep the heat from the sun out of the building. And then we also have some more unusual coatings like self-clean and antimicrobial coatings that we can put down using this technology. One of our leading products, though, is our NSG Tech product for PV. So when you're using essentially thin film photovoltaics, the first material you need is a transparent conductive coating, and we put down that in very large area for thin film photovoltaics. Basically, we're building the first part of the photovoltaic device on glass. And we make huge amounts of glass using this technology. So at this point, we have 4 float lines entirely dedicated to supplying the thin film photovoltaic market. So that's a huge amount of glass supplied globally. So as you can imagine, developing new materials and new technologies are a key development challenge for us to keep improving the performance of PV, and also, as I'll talk about later, improving our manufacturing performance is key in meeting some of the sustainability challenges that we have. The other coating technology we operate is sputtering. I'm sure everyone's quite familiar with the sputtering process. In this, we have sheets of glass, typically in a size of around 3,200 millimeters by 6,000 millimeters. So 3.2 by 6 meter size glass. We coat that in a semi-continuous process to produce both low emissivity and solar control coatings. That's a photograph of our PVD facility in the UK. That's in St Helens, next to some of our glass manufacturing plants. And yeah, that produces large jumbo-sized pieces of glass with multi-layer coatings on it. The most sort of popular, I feel, there's two types of coatings that are mainly produced there. One is low emissivity coatings, as I mentioned previously, to keep the heat in the room. Typically, for example, in the UK, regular low emissivity coatings are quite popular. Put them down on glass in a double glazed unit, that would go on the third surface. allows some passive solar energy to enter and the heat in the room to stay in the room. But of course, in hotter climates, we need solar control coatings. There we have what we call double silver coatings. And they're designed to basically maximize the visible light transmission and minimize the near infrared and UV transmission. And we have different flavors of those depending on the climate and how much solar energy you want to let into the building. But these are very complex materials. You know, a double silver coating can have, well, it says here 10 to 14 layers of material. Actually, some of our double silver materials have around 20 individual layers, with the thinnest layer in the coating can be even down to about 2 nanometers thick. So we're depositing 2 nanometer thick coatings on a width of 3.2 meters at quite high speed. And yeah, it's a very complex process. And again, you know, as you can imagine, we control and monitoring of that process is critical. And then when we think about where all these products go, we have a number of sort of important products that I'm showing here. You know, I talked about low E. We're also working heavily on building integrated photovoltaics. We have a collaboration with a company called Ubiquitous Energy, who make organic photovoltaics, which are semi-transparent. So these would offer around 50% light transmission, control some of the solar gain whilst generating electricity. In automotive, we have low emissivity coatings specifically for electric vehicles, because one of the key challenges in electric vehicles is how to deliver, how to keep the cabin warm in cold climates, because of course the electric vehicle does not generate heat in the same way that an internal combustion engine does. And so low E coatings are now very important for electric vehicles to keep the cabin warm in cold environments. We're also heavily involved in smart glazing. That's partly driven by our BIPV applications, but also in things like electrochromic glazing, where transparent conductive coatings play a role. But I think what we're seeing in terms of the built environment and also in automotive is that it's impossible to think about it in just, you know, solely as a glass manufacturer. Everything is becoming more integrated. So we've developed some smart glazing products that talk to the building control system and help control it by using sensor technology, and then power those sensors using photovoltaics, for example. But we also need a lot of different components there to make that work. So we're seeing a lot of fast-moving developments in architecture at the moment in terms of trying to make buildings more efficient, and we're very active in all of those. So, as I mentioned, you know, coated glass provides some really important functionalities in improving energy efficiency in the built environment, maximizing daylight whilst minimizing energy leaving the building. Solar control and photovoltaics are something that are critical. And then in transportation, as I mentioned, interior heat management is becoming more and more important in order to, you know, optimize the efficiency of climate control for electric vehicles. We're also looking at applying photovoltaic into the glass for vehicles too. I think the key challenge there is that the amount of energy you get from photovoltaics on a vehicle is a little bit, you know, there's not so much area to work with. So the energy generation is not so high. So the challenge there is coming up with nice integrated solutions so that we can use that energy generation potentially to cool the cabin or for some other parasitic energy loss. So again, that systems approach is important. So for the second half of my presentation, you know, we've given a reasonable overview of the different glass products and how they can contribute to sustainability. But I think one of the key challenges for us as a glass manufacturer is how to improve the sustainability of our glass manufacturing process itself, which as I mentioned, is quite energy intensive. So, you know, we have a large sustainability function within the company where we look at a number of different elements. You know, one is in the environmental aspect, where we want to minimize our greenhouse gas emissions, but in fact, you know, all of our emissions we want to minimize. as well as minimizing our ecological impact. And that happens by working with our suppliers as well, because of course, a number of the raw materials come from out of the ground. So we need to make sure that that's being carried out in a sustainable way. So we do look at all of the Sustainable Development Goals from the UN and try to work towards those. But we have a real challenge in terms of carbon neutrality. So we have a number of steps that we're looking at to become carbon neutral. At the moment, we use fossil fuel for combustion, so we have to look to minimize that. We do use some electrical boost in the melting process, but of course we want to try to increase the use of electric boost from sustainable sources. So can we use renewable energy to add more power to the furnace? We can't jump from our current process straight to full decarbonisation. It has to be through transition processes. So we're switching more and more to renewable energy. We're looking for new developments in the melting process to reduce our CO2 emissions. And then we're hopeful and working towards some more disruptive innovations, some of which I'll talk about, to really move towards that decarbonisation goal. We've signed up with the Science Based Targets Initiative to commit to reducing our emissions based on a 2008 baseline by 21% by 2030. And that's by reducing by improving the energy efficiency of our furnaces, using different renewable energy sources, and adding some new melting targets to try to improve that efficiency. So we've committed to this, and that's something that we're working very hard on right now. And I'll talk about some of the initiatives that we're working on right now. So there's a few different ways we can approach this. The first is by using more sustainable raw materials to reduce our CO2 emissions from the melting of raw materials. Another is in electric melting from green sources. We're also looking at the potential of hydrogen, which I'll talk about a little bit more later. And then on top of all of that, if even with these improvements we do not hit our targets, we then look at carbon capture and utilisation of that to improve our energy efficiency too. So lots of challenges to solve. And we have to do this all in a cost-effective manner because, of course, I think there's some tolerance to increases in prices, but at the end of the day, everyone has to try to make money here too. So the first thing is carbon reducing raw materials. So a number of the raw materials produced during glass manufacture are carbonates. So of course they emit CO2. So we are looking for new innovative ways to use raw materials which do not emit CO2 emissions. Things like calcined dolomite, which is something we're working hard on with some partners at the moment. And we'd have to, of course, produce that calcined dolomite using energy from renewable sources. So new batch material solutions are needed from our partners. We also need to increase the use of recycled glass or cullet because, again, two reasons. One is we can reduce the amount of fuel used with the increased use of cullet. We reduce the amount of raw materials needed, reducing the CO2 impact there. But unfortunately, it's not as simple as just taking any glass and putting it back in the furnace because contamination is a major issue for us, as is the composition of the glass used, because we carefully control the composition of the glass to ensure we get the right, composition of glass coming out. So something we're working hard on is in digital traceability of glass products and how we can, as we put glass out into the field today in a window or a solar panel, how we can understand what the composition of that glass is so that when it's time to recycle that glass, we know what we're putting back into our furnace and we minimize the risk. Another area we're looking at is in the use of electric melting because, that's a critical way to improve energy efficiency and ensure we're using renewable sources. The challenge is that right now electric melting doesn't provide enough energy to melt glass, so we need to improve that. We need new new ways to use electric boost in a furnace, but also using electric melting actually basically reduces the lifetime of a furnace. I've said that it wears out the bottom here in 6 to 7 years if we want to increase its use. Typically, a furnace will last for 15 to 20 years. So we have to come up with some new materials to enable the use of electric melting, and also new strategies to control the melting of the glass using electric methods, because that will change how the glass flows within the furnace. So we need new refractory materials innovation and new control systems to use electric melting. Another interesting area we're working on is in hydrogen gas firing. So typically we use natural gas. We had a world first about 2 months ago where we actually used hydrogen within the furnace to fire and test its use in melting glass. So there's a video, and what's very interesting, you can see the brightness of the gas flame versus the almost invisible nature of the hydrogen flame. And that's really exciting for us, but I think the challenge here is, well, one, where do we get enough hydrogen to be used in the furnace? We use a very large amount of material. We'll also need new process control strategies to allow us to use hydrogen, because it melts the glass in a different way. So how do we get hydrogen from a renewable source, which is of course very important. Green hydrogen is key here. Carbon capture, there are existing technologies for carbon capture, but none suitable quite yet for use with flue gas from a float manufacturing line, because with relatively high impurities relative to the carbon content, and so that causes some issues. Also, doing it cost effectively is difficult. Finally, thinking about advanced manufacturing, both the coating and the glass manufacturing process is highly complex. And so we're exploring with partners ways to use machine learning to improve manufacturing efficiency. We generate a lot of data from both our coating and glass manufacturing processes. And so using that data, how can we improve our manufacturing processes? We have a lot of work ongoing in that area at the moment. Finally, another thing to think about is how to use machine learning to accelerate innovation. As I mentioned, transparent conductive coatings are a really important need for the NSG group in Pilkington. So we work with the UK innovation agencies to help us sort of identify partners. And one such partner is the University of Liverpool Materials Innovation Factory and the Hartree Centre. And we're working with both of these guys to help us develop new materials through leverage funding. We're basically using a machine learning approach and the materials expertise of the University of Liverpool to come up with new materials for transparent conductive coatings, which can hopefully improve what comes out of our coating processes to make more efficient solar cells and more efficient coatings for use in the applications I've mentioned. So we've really, with machine learning processes, we have the potential to shorten our materials discovery. So just in conclusion, glass is playing a vital role in maximising the energy efficiency of the built environment, whether that's buildings, whether it's automotive, or whether it's PV. Another advantage of glass is it's long lasting, and we're always looking for ways to improve that, but it's also recyclable. You can put it back into the furnace. And those functional coatings I mentioned enable new technology development, but they're very hard to control, and we spend a lot of time getting a large scale, highly controllable process. And finally, for sustainable manufacturing, we need innovation in many different fields, and it all needs to come together to help us achieve our goals. So we're really open for collaboration and ways to work with partners to meet some of the challenges I mentioned. So yeah, thank you for your time. I'm looking forward to discuss later.
Brilliant, Neil. Thanks very much. If we can, Nick, can you share your slides?
I'm just waiting for Neil to drop off, and then I'll have a go.
Brilliant. And then we'll pick up questions in the panel. There's also a couple of questions appeared, Neil, in the chat there. You could maybe, if they're answerable, just as you can fire back to Peter.
Yep, sure. I'm having trouble stopping sharing. I apologize. Stop share. Okay, there we go. Sorry. There we go. That should be it now. So let's see in the chat. Okay.
Okay, Nick, whenever you're ready, the floor is yours.
No problem.
Nick Butcher from, sorry, Nick, I forgot to introduce you.
It's no worries about that, Adrian. I'm Nick Butcher from Emerson and Renick. We're a roll-to-roll manufacturer. So what I thought I'd do is I'd give an industrial roll-to-roll perspective from a SME on how we're going to adapt to some of the climate change deliverables that COP26 is going to throw at us. Just a little bit of background there. I sit here as the Process and Equipment Development Director. My background is I've had 20 years in developing roll-to-roll solutions and transposing issues and R&D from wafer scale technology to wide web technology. So what I'd like to do is just give a little bit of an overview about who we are and our expertise, a bit about why we're changing and how we are changing as a business, and we have to change if we're going to survive. Then I'm going to have a bit of a deeper dive into some of the techniques of coating across wet chemistry and vacuum coating, and how a lot of these coatings that have been talked about today will actually be developed and morphed into roll-to-roll modes. The need for roll-to-roll long term is to drive down the cost of manufacturing, and I want to show you how we're getting involved with doing that. And then I'd like to finish on a bit of a good news story, which is the amount of development that is currently going on in this area and how a lot of these next generation technologies are being considered by the industrial manufacturer. Okay, who are Emerson and Renick? Well, it's suffice to say we're actually better known in Silicon Valley than we are in the Hindburn Valley. We're a 103-year-old private business, actually, of which we have 6 major shareholders, all working directors, of which our second biggest shareholder is the 172 employees in the business. So we feel we're still a very, very active family business where we take in the account of the direction of our employees. We are active across several markets and we are primarily a roll-to-roll manufacturing machinery provider. We don't actually make a lot of the products, but we provide our expert overview into helping companies decide the machines that make it possible. We've got a long proven track record in development of new and existing machines on emerging technologies, and I'll touch on some of them. And we do a lot of refinement to what we do there on our products to remain recent and relative to what we're going to do forward. What is clear is we've got our global spread and we're starting to grow that further and further afield. We've got 2 key locations in Accrington and north of Accrington where we have our HQ. We design, manufacture, build and service a lot of our equipment, and we're quite unique in respect of our peers and our competitors insofar as we're still very vertically integrated. By that, I mean we still design, we still manufacture, we still build all our own rollers, our side frames, our electrical panels, we test and assemble, we make all our own software, and we very much keep all IP in this area under one roof. We've got pilot and manufacturing facilities in America where we have the ability to manufacture, build and service and provide sales support. We've got pilot coating facilities as well in Austin where we support research programs out there with the Nascent Center. We've got a footprint over in Zhuhai in China where we have a sales and service center, and then in India as well. Both these markets particularly emerging when it comes to the investment internally on renewables, and we're very much in and among that as we go. So a bit nod to the past, and why is this relevant? Well, E&R was set up 103 years ago in what at that time was the hotbed of developing wallpaper manufacturing. It started with the leather cloth, and it's a lot of this expertise that we have today is generated by the nod to our past. East Lancashire was a very wet area of the world. It could wind the finest threads, and it became no surprise that some of the expertise in wallpaper manufacturing and so forth of going wide web paper handling developed here because of the skills that are local, with the expertise of drives companies, handling companies. Through our past, there's been a lot of diversification, and we've been at the front of a lot of world firsts to some extent. In 1972, we were the first to develop in-register hot embossing, and today we're still a world leader in that in the wallpaper market. In 89, we were the first to introduce shaftless in-register gravure presses. Then acquisition's been a key part of our growth as well. In 2002, we acquired the Dixon Group. Dixon were an even older company, those who developed some very advanced coating machinery, which were important in the magnetic tape media when CDs were being pressed. And then in 2014, we purchased our biggest competitor in the automotive sector. 2017, we secured our largest orders when we developed into the vacuum coating line, and they were based around scaled platforms for solar and flexible electronics. And then more recently, we've celebrated our centenary and a rebrand. So what do we do today? We design, we engineer, manufacture and support products which are in most of the components that you find in everyday products. We're heavily involved with developing solutions in automotive, in aerospace, consumer electronics, home decor, the solar industry, and many more. And just some examples there is we're already making roll-to-roll systems for flexible solar cells. We're doing functional layers for next generation wearables. We've been heavily invested over the last 8 to 9 years in micro batteries and wet chemistry batteries for LFP, for solid state, and we're working heavily with a lot of companies in there. We do a lot of work in optical layers for augmented reality headsets, for solar control films for buildings and vehicles, and then in carbon fiber composite coatings as well. We achieve this spread and knowledge base across 4 different companies within the group. We're split as E&R Print, E&R Coating, E&R Forming, and E&R Vacuum. In the area of the print world, we build very large turnkey lines. So wall covering typically and floor covering would take the bulk of this area. But that area in itself is also very thirsty. So we're working on next generation techniques to reduce our carbon footprint alone, not just in the way the end products are got to market, but we self-analyze on the techniques that we're using. So we're trying to get rid of thermal oxidizers. In this instance, we're trying to get rid of the big ovens, and we're working with companies on UV printing, digital printing, and shortening the footprint of these types of machines. In the coating world, I could probably do 1,000 slides on this area of the business, but suffice to say, we develop functional materials and layers onto flexible substrates at lab scale, pilot scale, and production scale. Typically, machines that we would produce would be anything between 300 millimeters to 3 meters web width. And we do that for multiple different ways of taking full turnkey solutions, including the coating, the laminating, the drying, and then in some cases, we'll actually make them as roll to piece. In our forming section, we make automotive heat exchangers and tube forming and fin forming with assembly for aerospace and automotive. And what this is doing is taking very, very large reels of aluminium, titanium, and then forming them and coating them to make very, very complex heat exchangers. So when earlier in some of the presentations where there was referral to coating technologies there, we're already applying them, but the expertise that is already established in the heat exchange mechanisms inside automotive vehicles isn't yet made its way to heat pumps and other technologies that in the future could benefit from this. So we're working heavily there to assist some of these other disruptive technologies now, gain the benefits of a lot of the lightweight manufacture and speed of production of automating these processes. And then in the vacuum arena, we build some very, very large scale machinery, again, for doing functional coatings. And we put together solutions in both wet chemistry and vacuum to end up with very viable products and test these in the market. So as a change of focus, we're transferring, my outlook is to look at transferring the nods to the past and the expertise that we have, and how can they benefit the next generation technologies, and want to address why we're changing our change of focus there. And I split it into three main reasons when I justify this to my board when I'm requesting further funding in the R&D section. We've got our moral obligations, our legal and our financial. So how are we doing that? Well, on the moral side, our customers' requirements are changing. More and more large organizations are passing on the expectation to us as suppliers that we must support their scope 1, scope 2, scope 3 as part of their pledges. So it's important that we meet the needs of our customers and our in this respect. But not only our customers, our employees, they've got expectations and ambitions as well. And it's important that we focus on what they would like us to be. They're an essential part of our business. We've been around 103 years, and the reason for that is we have a very tight relationship with the employees, and we may have to make sure that we're meeting their expectations. To do that, we will redefine the mission statements of the business. They have regular review, and they need to take an account of that. Our aligned leadership is aligned with the aim of COP26 and the outcomes. And to do that, we have to have an evolving company culture and an outward appearance. Legally, we're going to see refined legislation. I sit there expecting the COP26 conference to set new limits and new machinery directives, which as a provider we must meet. We'll need to review the practices and procedures internally to make sure that we're meeting our legal obligations. And we're seeing more and more recruitment needs into the compliance roles for our business to remain ahead of the curve, to understand the needs of each of the individual markets which have come out of the machinery areas we serve, and how that impacts us as machine builders. And of course, financially, this level of diversification is going to provide opportunity. We'll get new markets and territories because COP26 is going to put in pressures on countries worldwide, some of which we're not yet working in, but make ourselves known. It's going to foster a proactive approach to partnership and development. And it's important we share this expertise, and through this, probably shared financial risk. We know we can't do it all on our own, and therefore it's important we develop strategic consortia and really get a grip of this where we can share our knowledge. And it will drive new product development, which again puts financial burden on industries, but we know we need to do it. So taking some of the machines from the past, we're heavily focused on transferring their manufacturing techniques into energy storage, including batteries with solid state and wet chemistry. We're working in collaboration there with the companies like Faraday, with the UK BIC, of which we're working with British Volt and Johnson Matthey in a consortia to develop some of the gigafactories that the UK is committing to. In the area of fuel cell, we're transferring our knowledge into platinum group metal replacement layers, and we're working with developing porous transport layer and membrane systems to run ever thinner membranes around the 6 micron and less range. In the solar and photovoltaics, we're working heavily to develop thin film CIGS-based back and top contact layers. We too are working with solar control films, but transferring some of the technologies that NSG develop on glass, we're moving them onto polyesters and so forth. And in the area of electrochromics, we've done a lot of work there to put down multiple layers. In the area of fusion technology, we're working with companies to look at developing superconductor tape manufacturing for tokamak reactors. In this instant, we have to develop very thin layers, and we have to develop them at very high speed. And hopefully that will provide a more sustainable energy development using nuclear energy. And then a responsive method is in pathogen. And I know Sarah, who will be following me on one of the talks, she's provided some insight into the work that's going on in that area. but it's suffice to say us at a machinery level are developing solutions for antiviral and antimicrobial coatings, which are almost an outcome from if the cost of global warming and the effects of more virus and pathogens getting out there. So quick into the expertise we'll transfer. So our background on atmospheric coatings is in print coating, including gravure, screen, flexo and inkjet. We can provide embossing and imprinting solutions, which will be relative to the structuring of some of these nano materials that we want to manufacture at mass production. We've then taken it one step further, and we've taken traditional mechanical embossing, which we have some very, very high accuracy, and we're supporting that with more advanced nano imprint lithography. And in these areas, we're actually pushing the envelope to take roll-to-roll solutions that today exist in the semiconductor world down at the 50 nanometers and less. And we've just developing machinery now in roll-to-roll that too will allow us to coat down to 0.5 micron wet with a dry coating to leave us at 50 nanometers in some of our structures. The web conditioning is important because a lot of these surfaces that we all want to coat, we want to develop, are dirty. And so we're working heavily to develop web cleaning in contact and non-contact. And we do that using corona and atmospherics. On the coating world, we've got a very, very large, diverse range. I'm not going to go into each of them now, but you can see some of the different types. What is clear, we have to focus on drying and curing, and not just the art of us producing the drying and curing techniques, but developing new solutions with low energy needs. In this case, UV curing is becoming much more relative. So it involves us working with ink manufacturers to develop solutions. Near infrared, electron beam, and selective IR is as well becoming. So we can get rid of some of the big thirsty gas-fired ovens and focus on low energy techniques. In the vacuum world, very much like Neil, we focus heavily on a lot of the PVD. In that area, we're working for solutions developing e-beam, thermal induction. We also do a lot of work on sputtering as well, using both planar and rotatable. We've done a lot of work recently transferring roll-to-roll semiconductor printing using reactive ion etching, and that's where we can create very high aspect ratio structures, and we know we're going to need them for manufacturing some of these next generation products, and I'll talk with that just a tiny bit further on in the presentation. On ALD, we partner with Benec to develop roll-to-roll solutions, which are used in both coating layers for barrier layers, but they're used in active layers in battery structures and other layers that are very, very relative to low carbon manufacturing. And then we also work heavily on CVD. Again, web conditioning in the vacuum world, we cover that. And then we're also developing in high speed in vacuum demetallization and patterning. We don't forget about the ancillary, which is a lot of work on metrology with a heavy focus for building industrial systems that need camera systems for defect detection. We're looking at coating weight, optical spectrometry, and any manner of analysis that has to be built into the machines. And then further down the road, we're looking at the post-processing in calendaring, sheeting, stacking, and the effects of these processes on the coatings. My main role is to look at the production challenges and mitigation strategies and how we transfer these techniques from the lab scale to the production scale and where we can do that in roll-to-roll. And in some instances there, some of the images you can see multi-layer NFC type, which I print in, which is also used in small scale batteries for micro batteries. And then in the instance of the roll-to-roll coater there, we're actually handling 6 micron foil there as part of a battery for a solid state battery where we're trying to reduce the parasitic mass. But the key thing is we're heavily focused on developing mitigation strategies to allow this to be scaled. How have we done that? We've spent a lot of internal investment. We have looked at using facilities provided by some of the government facilities out there, but we've decided to go our own route, and we've developed our own technology center in there, which is open for both our own and our customers' process development. We've got vacuum coaters, pilot coaters, and multi-stage flexo and forming presses. We've developed laboratories, and we've invested in people. What's been key to this is that we can develop these processes in collusion with the universities, in with other companies, and open up in our facilities. And to that extent, we're heavily involved with Horizon, UKRI, Innovate and EPSE programs. At the moment, I've at least got 7 to 8 live projects going through my facility, and we're always open to discuss with new opportunities, with new partners all the way who's interested in checking out roll-to-roll scaling of these technologies. To that end, we have in-house vacuum coating machinery where we can test up to 500 millimeters wide using sputtering, chemical vapor deposition, reactive ion etching, and electron beam gun deposition. We've got inline spectrometers, we've got other impedance control systems, so we can help take these to find out how they would be productionized. The same state, we do this in atmospheric coatings, so we can combine both our atmospheric expertise with our vacuum expertise and look at the viability of products. It allows us to test sensitive substrates, in the case of polymers, foils, flexible glass, and how these will handle, because it's okay us making them at the small scale, but we need to see the combined effects and mitigation strategies of what we would have to do to manufacture these. We've invested heavily in the laboratory side, and into this end, we need to be able to see what we're doing. So we've brought in-house our own scanning electron microscopy. We've brought in any number of spectrometers and thin film profilometers, so we can actually look at the structure of coatings. We can see how they perform, we can see how they bend, and it allows us to move very, very fast with our own internal developments by having this ability to turn this opportunity on and share this with our customers. So in the end, and I think this is the good news story, we've been working heavily on this in the background over the last 10 to 15 years. We're developing larger area roll-to-roll solutions which to suit a wide range of processes, and we look at our design and scalability of all our techniques across a wide plethora of low carbon manufacturing. We design them to be suited for a large area of substrates, and like I said, we're scaling these to 3 meters wide. The idea is that with big industrial open control platforms, with good, strong partnerships out there and good repeatability built in, we can create wide-ranging machines that will enable some of these technologies for the future. And in some modes there, you can see large area sputter coaters for solar cell manufacture. In the top right, these are ITO replacement layers using atmospheric techniques and very tight environmental control, where we can cut down the need for very large dry rooms and create localized, low-cost rooms. In this area, we've got 2 meter wide separator films being coated with chemical vapor deposition. We've got lithium sulfide battery coaters. We've been developing solid state vacuum coaters with combinations of electron beam and sputtering. And in the far instance here, you can see the scale that we're actually nano manufacturing silicon pillars for graphite replacement layers in silicon anodes, where you can see the scale where we've successfully printed in roll-to-roll down to the 50 nanometer scale. So on that note, I'd like to thank the DSM for inviting me to speak today. I'd very much like to have the opportunity to meet with any of you if you go to COP26, and I'd be happy to take your questions on the panel discussion later.
Excellent, Nick. Thanks very much. I think that the last 2 presentations there have given us a lovely view from the industrial side of the challenges, and then the opportunities, and then the work being undertaken and the work planned, all in relation to sustainability. So we move on to an additional phase of the program now, and I'll hand over to Ash and Swarab, who are my our co-directors on the network.
Thank you, Adrian. Very interesting presentation so far, and I'm sure there will be a number of questions in the Q&A sessions and beyond that. Let me introduce myself. My name is Ash Tiwari. I'm Royal Academy of Engineering and Airbus Joint Chair in Digital Manufacturing in the University of Sheffield. I'll be hosting this last session along with Saurabh from LSBU. The next session, I will immediately move into that. It's a very special session. It's a set of presentations from our early career researchers, from PhD students. And they have been very carefully selected. We had an early career researcher event organized a couple of weeks ago, and these were the top 3 presentations that were selected from there. So I hope it will give you some insight on what research is going on and what the views of our early career researchers are. So without any further ado, I'm going to immediately start Nestor to share his slide and start the presentation. Saurabh, would there be anything you would want to say at the start?
No, Ash, that's fantastic. So in continuation to what we just saw about roll-to-roll manufacturing, we will begin by seeing what digitalization can do to roll-to-roll with the presentation.
Yeah.
Okay, good afternoon. Okay, are you able to see my screen?
Yes, we can. Yes.
Okay, thank you very much. Well, thanks a lot, Professor Ash and the rest of the panel. Good afternoon. I am Nestor Sanchez, a first-year PhD student from the University of Sheffield. And today I will cover this topic, which is the role of digital platforms in decarbonization. In the excellent previous presentations, we have seen the drivers behind digitalization. The Paris Climate Agreement brings an economical and social transformation to decarbonize the industry to achieve net zero gas emissions by 2050. It is also understood that human driver is the major contributor of the global temperature rise in the last decade, causing the well-known environmental effects of Earth overheating. You may be thinking, what is the technology role in this scenario? How does it fit? Let's think in this word, digitalization. Digitalization is more than a simple definition. It comprehends a framework which consists in infrastructure and market changes along with digital transformation, which together are aligned to the decarbonization goal and to the Industry 4.0 strategy. From this perspective, the digitalization presents the following benefits. Decision-making. There is no other more valued feature for organizations than being able to take fast and accurate decisions based on real-time data. By being able to see real data, it is possible to monitor performance and track parts and products through a manufacturing system. Through the use of embedded sensors in a product, the product lifetime can be extended by tracking, monitoring, and forecasting maintenance requirements. And finally, end-of-life strategies as disassembly and recycling can be improved or created to help in the decarbonization goal set in the Climate Agreement of Paris. So what is digitalization from a technology perspective? It is being able to represent in digital form all processes by which products are produced. Let's take a look into a digitalization example of a roll-to-roll system concept, which is being developed by the University of Sheffield. The roll-to-roll system is widely used in the flexible electronics sector and enables functional coating deposition in a roll-to-roll fashion. In this case, our output will be the coating thickness in nanometers and coating surface quality, which means free of cracks, voids, or other surface disturbances. Now let's see some of the inputs. First, we need to understand the tension control for unwind and rewind zones. In this case, we need to calculate the roll radius to be able to calculate tension in an open loop fashion, and we can use load cell sensors to measure the real tension in the system to compare calculation versus real data, and convert it to a full closed loop control. The speed control is measured by an encoder sensor directly affected by the coefficient of friction of the roll and the material of the web, which can vary significantly. The input and output tension in this section also plays a role in the velocity control feedback. Depending on the vision sensor to be used, the positioning of the system affects directly to the coating scan. In this section, artificial intelligence and machine learning can be applied to recognize defect patterns. These are just some examples of the input basics that must be considered to digitalize a system. You may wonder, what could happen if all these parameters are not understood and not sensorized? We will have defects as floppy web, waviness, voids, fluttering, among other related failures. By digitalizing any system, we can do in situ measurements, which will allow us to detect defects and disturbances on real time, producing less scrap and being more eco-friendly. As previously shown, we can infer that digitalization and the transition to digital platforms comes with diverse challenges. Technology complexity. All systems have their own and unique complexity, either to dimensions, cost, product nature, or technology limitations. Digitalizing a system is not an easy task. Additionally, and from a wider perspective, global policies and political implications must cope with the speed and the need of new strategies to do efficient implementations. Also, the value chain transformation implies cost of adaptations, which not all the companies are willing to afford. All these challenges triggers needs for further research. We must consider that digitalization has its own environmental risks, talking about its respective needs of resources and energy. This must be monitored to avoid causing a major problem during implementation. The speed of digitalization and the transition to circular economy through Europe and the world needs to be measured as and understood as a whole to ensure the success of global decarbonization, and the potential to scale up and digitalize the existing architecture and technologies are an open topic for further research. Definitely, strong collaboration among all of us is the key to success. It has been an honor to share the stage with all the team gathered today, and I would like to thank you all, and please remember to keep in touch. I will now return the control to our host.
Thank you, Nestor. Nestor, we'll immediately move to the next presentation, but I would encourage you to have a conversation with Nick in more details to share the work that you have been doing. I can see there is a very interesting crossover there. Thank you, Nestor. Nestor, if you can stop sharing. Sarah, can I please invite you? Sarah's presentation is on engineering biology, and she's going to talk about how that will have that can potentially address climate change. Sarah, over to you.
Thank you, Ash. Hi, I'm Sarah. I'm a PhD student at Cranfield University. I'm working under the supervision of Dr. Saurav Goel, and I'm here to talk to you about engineering biology and how it can help us address one of the most threatening impacts of climate change. So our planet's carbon cycle is out of balance, but that's not our only problem. We are all familiar with climate change and it being predominantly the result of CO2 accumulating in the atmosphere and inducing rising global temperatures. We are even witnessing the consequences firsthand through extreme weather events all over the globe. Such a big planetary change also threatens oxygen availability, as oxygen levels have been on a steady decline. The projected changes in weather patterns and climate will also reduce water availability, and it will affect the water distribution. This will lead a projected 2 billion people to resort to the use of unsanitary water sources. Now, these three factors will create a certain thermodynamic state that would be a host for a diversity of dangerous pathogens that are unheard of as of yet. We're already witnessing the rise of superbugs through the emergence of and spread of antimicrobial resistant pathogens. Now, what is antimicrobial resistance? Put in simple terms, it is when microbes no longer respond to the antimicrobial drugs that are used to treat them. And this resistance occurs naturally, but very slowly. However, due to a variety of factors, one of the main ones being the climate change driver, this resistance and resistant infection transmission is heavily accelerated. And new drug innovation is lagging behind. AMR is a threat to global health, to food security and development, and if it is not mitigated in the near future, it is projected to kill 10 million people worldwide per year by 2050. Mitigating AMR has many levels to it, starting from the responsible personal use of antimicrobials all the way to governmental, national, and international responsibilities, specifically in supporting research in promising areas. One of the areas that is and will continue presenting very high impact pathways and innovations with regards to combating AMR is engineering biology. Engineering biology is the creative, innovative interspace between engineering and biology, and it has already contributed heavily to the advancement of healthcare and healthcare research. Some of the examples are the development of biomedical implants and patient-specific implants, microneedles, which have a variety of applications, including disease diagnosis and treatment, and organs on a chip, where therapeutic response of organs, tissues can be studied to model organ response. Generally speaking, engineering biology is built on three main pillars or research areas. The first is bio-inspired design, novel materials, and bioengineered cells and systems. And all of them can be exploited to tackle the problem of antimicrobial resistance. Combating AMR through bio-inspired design comes in the form of prevention of surface contamination and the fomite spreading of microbes. The main idea is to design a surface that can either stop the microbes from adhering, in this case it will be called a anti-biofouling design, or try to kill the bacteria or microbes as they try to adhere. And in that case, the design will be called mechanobactericidal. These kinds of surfaces can be used in a variety of applications, such as in transport, in food packaging, and in healthcare, including for use in surgical tools and biomedical implants. Innovation in materials and material systems can also heavily contribute to solving the AMR problem. And a few of the main areas of interest at the moment are antimicrobial peptides, antimicrobial nanoparticles, vaccines, and chitosan. And all of these are very promising antimicrobial like replacements for antibiotics that we take at the moment. And a very interesting method that is being currently explored is called quorum quenching, and it uses specific enzyme coatings that intercept or degrade the signals that the microbes use to communicate with each other. So this method basically creates that space for the host immune system to come in and attack these microbes before they try to establish any virulence, and it will help, the host immune system will eradicate the infection. For the bioengineered cells and systems, which is the third pillar of engineering biology, it can boost the fight against AMR through quantitative modeling and synthetic biology, by, for example, making biosynthetic gene clusters to understand and predict pathways of drug resistance and hopefully try to mitigate them. It can also help through bioengineered delivery systems that would employ targeted drug delivery, which can reduce AMR significantly. To conclude, we as a species are experiencing several existential threats, with climate change being the main driver. Scientific research has a track record of getting us out of ruts like this, most recently experienced with the COVID vaccine research and treatment. That is why, more than ever, supporting and accelerating multidisciplinary scientific research should be our top priority. Thank you for having me.
Thank you, Sarah. And with that, we move to the last presentation of the day. It's from Syed from London South Bank University, who's going to talk about machine learning and its role in handling and tackling climate change. Syed, over to you.
Adam, thank you so much. Just give me one moment. Can you see my screen?
Yes, we can now. Yes.
Brilliant. So good afternoon. My name is Syed Hussain. I'm a first-year PhD student at London South Bank University, and my research is on CFD simulations of pathogen-laden saliva microdroplet propagation in an office environment. This is supervised by Dr. Saurabh Goel as well. And today I'll be talking about machine learning for sustainability and climate change. So machine learning can be used in a variety of ways to predict, monitor, and optimize human processes and the effect that we leave on the planet and its ecosystem. It can be applied to many sectors, almost anything that requires digital management or that could benefit from digital management. Sectors that come easily to mind are transportation, climate prediction, and farming and forest management. But other sectors such as energy production, building management, and even geoengineering can be considered when discussing machine learning. So one of the three topics, the first is autonomous vehicles. They are still in their infancy, yet they provide one of the most tangible effects of reducing climate change. The likes of Tesla, Optimus Ride, and Uber are heavily investing in autonomous vehicles for private and commercial use. And amongst the other advantages, such as reducing the chances of road traffic collisions and an always alert driver, one of the most compelling advantages of AVs is eco-driving. Vehicles that can communicate with each other can also accelerate and decelerate simultaneously, which would eliminate the sudden peaks of heavy acceleration and the subsequent unnecessary braking, ultimately saving fuel and reducing emissions. In commercial vehicles, there is an added benefit of increased fuel efficiency by platooning. This is effectively trucks reducing their air resistance by driving incredibly close together, accelerating and braking together, that would only be possible with autonomous vehicles. Next, we have automated afforestation. This is the practice of planting trees in new places, and it's a form of long-term CO2 sequestering. And theoretically, up to 900 million hectares of tree coverage could be added worldwide. However, it has to be ensured that there is a positive impact when planting the trees. Afforestation at the cost of a carbon sink ecosystem could result in a net increase of greenhouse gas emissions. Wide-scale afforestation requires due diligence towards local biospheres and how new trees could affect native species, and obviously vice versa. And so machine learning can be used in automating large-scale afforestation by monitoring and examining numerous sites, looking at plant health, assessing weeds, and then selecting the optimal space and time to plant the trees. And so countries like China could benefit massively from automated afforestation, as their future agricultural independence depends on their afforestation program. And finally, we have material science. There's a constant endeavor to create better materials for a range of applications. However, the process itself can sometimes be slow and imprecise. The physics behind materials are not always completely understood. So often humans apply heuristic methods to understand a proposed material's physical properties. An example of a heuristic method such as trial and error can ease cognitive loading during decision making, but at the cost of either resources, time, or a combination of the two. Machine learning can automate and accelerate this process by combining existing heuristics with experimental data, physics, and reasoning to apply and possibly even extend existing physical knowledge. And so techniques such as supervised learning, deep learning, and generative modeling can be used to synthesize, model, and design new materials, such as new solids for lithium-ion batteries, or materials that can better absorb CO2, or alternatives to cement production, which as an industry would be the third largest CO2 emitter if it was a country behind China and the United States. That's all for me. Thank you very much for your time and attention.
Thank you, Syed, and thanks to all the student speakers and all the speakers for today. I'm mindful that we have run out of time for the session. We mentioned a closing time of 12:30. So what we are going to do is we are going to immediately start with the panel and the Q&A session, and we will start with the questions that have already been asked by the presenters. And I think that will give the opportunity for people who have already asked the questions to be able to get response from the speakers. So sort of if you can go ahead with the questions in the chronological order, that would be very good. Thank you.
Thanks, Ash. So I'd like to begin first to reiterate on the questions that were already asked, as Ash suggested. So first question came from teacher DMV to the time when Margaret, when you were presenting. So the question is, what specific composite coating materials have you developed or identified through your EPSRC project as being suitable for wind turbine applications? What were the specific metrics and what was the reinforcement phase?
Okay, sorry, can you just repeat that question again?
Yeah, Margaret. So the question reads as what specific composite coating material have you identified through your grant as being suitable for wind turbine applications? What were the specific metrics and what was the reinforcement phase?
Okay, so these were glass fiber reinforced materials, but what we found was that these things are generally coated with a composite, with a polymer based coating. So it was just a very we just looked at a very simple sort of epoxy layer on the surface for the polymer coating.
Okay. Thanks a lot, Margaret.
Yeah.
There'll be any follow-on question, then that can be asked. So the next question to Neil, as you can see on the screen, formula is sharing. How do you check the uniformity of thickness in your multi-layer stacked coatings deposited by the PVD process?
Yes, so in a couple of different ways. So in manufacturing, we have optical monitoring positioned at key points within the manufacturing process. So we can measure the color, light transmission, reflection, but also things like the sheet resistance. And that we can then take that data and use our optical modeling software to basically figure out what the uniformity of the layers are and then make any adjustments needed. Now, of course, before that is able to be used, we need to fully characterize the coatings. So then we would use, individual layer deposition. We'd look at the thickness of that using depth profiling and yeah, typically just optical measurements, UV, vis, near infrared. And from that, you build a picture of our different materials, and then we can plug that into our models to control the process.
Okay, thanks a lot, Neil. So we have although come to the thoughtful close of the time, but I'd just like to personally say thanks to all the speakers. As I said, they have really put great efforts to put on this show for today. And I think from the variety of events we had, there was so many things we could go on to discuss, but time is always of essence, which is the case here. So if there's any other questions somebody want to ask, can quickly ask now. I'd like to otherwise hand over to you, Allan, for finally giving some closing remarks for today.
I would just reiterate the thanks that everybody's given for all the speakers. It's been a great session, and it really has illustrated the diversity of topics that are involved in researching climate change issues. And I think we as investigators are all delighted about the way it's gone. And all I can do is just thank everybody again, not least the students for their excellent talks. So to keep on time, I think we can wrap it up.
So thanks once again. And if there will be any further questions, they can always be emailed to Pamela through the network, and we will try to facilitate all the discussions with the potential speakers. And we also look forward to engage further in other events with all of our nice speakers who have really made this day really brilliant. Thank you, everybody.